In this example, we have a heterogeneous reaction, namely a solid reacting with a gas to form another gas. And we want the equilibrium composition at 1 bar and 25 degrees C. We start out with 10 moles of carbon, 5 moles of hydrogen. So first thing we need to do is calculate the equilibrium constant, which we calculate from delta G of reaction. And so delta G reaction at standard conditions is just the delta G of formation of the product, heptane, minus delta G of formation of the two reactants. Now, because hydrogen and carbon are elements, the delta G of formation are 0, and so this just becomes a value we can look up at a table. Since we're at 25 degrees C, this is 8.2 kilojoules per mole. So now let me rewrite the equation, and then we'll look at the extent of reaction to indicate how many moles we have at equilibrium. So we start out 10 moles of carbon, 5 moles of hydrogen, 0 moles of normal heptane. So this is the start moles. And then at equilibrium, we'll use this Greek symbol psi for extent of reaction. So this is moles now at equilibrium. Now in the equilibrium calculation, we're going to need to use mole fractions to calculate partial pressures. At these conditions, we're going to assume ideal gases. And so the mole fraction means we have to calculate the total number of moles. So the total, and keep in mind the total gas phase moles, because the solid doesn't affect this gas phase composition. So 5 minus 8 for hydrogen plus heptane. So the 5 minus 7 times the extent of reaction. That's the total number of moles. So now what we want to calculate is the mole fractions in the gas phase. So of course carbon we don't calculate. This is 5 minus the extent total number of moles, and likewise here. So now we're set up to substitute into the equilibrium expression. The equilibrium expression, it's ratio of activities, ratio of fugacities. We're looking at ideal gases, so that becomes the fugacity divided by 1 bar becomes the partial pressure of the heptane, because ideal gas. The activity of carbon over the activity of pure carbon is 1, and then the partial pressure of hydrogen, and the partial pressure of hydrogen is raised to 8th power. And so partial pressures are mole fractions times the total pressure. Well, the 1 we won't have to carry through. Mole fractions of hydrogen to the 8th power times the pressure to the 8th power. Keep in mind the pressure has to be units of bar, because that's our standard state fugacity. And so then I can simplify this slightly. So now I can substitute in these two mole fractions, and the pressure is 1 bar, which makes the calculation easier. So let me pause and substitute in the mole fractions. Let me also substitute in equilibrium constant. So the equilibrium constant is going to be the exponential of minus the Gibbs free energy change for reaction in standard conditions over RT. And now I'll substitute in the mole fractions on the right side. So I've rearranged, simplified, and this of course is the pressure 1 raised to the 7th power, which is of course still 1. Now I can substitute in values for delta G that we calculated, and the temperature, absolute temperature on the left side, and then I'll have a nonlinear equation which I have to solve. So let me calculate the equilibrium constant. So I converted delta G to joules instead from kilojoules, and absolute temperature for 25 degrees C. I get this equilibrium constant, so this equilibrium constant is equal to the right side of the equation here. So this is a nonlinear equation. What I'm going to do to solve it, I'm actually going to use a polymath program and solve it in polymath. Essentially what I do is give myself a little more room here. I say I have a function that we want to equal 0, and so I'm going to rearrange the equation slightly, take the denominator to the other side, and then move the term that was on the right side, the numerator, to the left side. So I have an equation now that's equal to 0, and this is how polymath would solve it. When I substitute in the polymath, it gives a value for the extent of reaction 0.1201. is 0.12. And this accuracy what we're doing. So this means we can calculate now the mole fractions by just substituting back into these values, and we can calculate the number of moles of carbon. So for carbon, number of moles 10 minus 7 times the extent of reaction, and this is 9.61 moles of carbon are present in equilibrium. Main reason for doing this calculation is to check that we didn't use up all the carbon. For example, if we had started with a half a mole of carbon, we couldn't get to equilibrium to satisfy this equilibrium expression. We'd have reacted all the carbon. So this is a check on the system. The mole fractions, if we substitute in, and I'll pause and write down to calculate the mole fractions in the gas phase. So see, the amount of reaction is pretty small equilibrium constant, and the mole fractions have to add to 1, but I did a check also, verified that indeed the calculation for the mole fraction by substituting extent of reaction for hydrogen gives the same number. The only other check I'm going to make here is to look up the saturation pressure for hexane at 25 degrees C, because this calculation assumes that all of the hexane stays in the gas. And so the saturation pressure, 0.061 bar, and the pressure of hexane that we calculated at equilibrium is the mole fraction of hexane times the total pressure, 1 bar. So that's then the partial pressure. Partial pressure is less than saturation pressure. We don't have any liquid condensing.